Have you ever stopped to think about what makes your microwave beep or how your remote control just works? It's not magic, you know. There's a tiny, hidden brain inside pretty much everything, and you've probably got dozens of them around you right this second. Today, we're going to pull back the curtain on this unsung hero of our electronic world. I mean, seriously, think about it for a sec. One gadget is nuking your lunch with microwaves. Another one is sending invisible signals through the air to your TV. And your car is managing thousands of tiny, controlled explosions every single minute. These things could not be more different, and yet they all rely on the very same kind of technology, a little dedicated brain whose only job is to tell them exactly what to do. And that brain is a microcontroller. Now, this is not like the processor in your computer, which is a jack of all trades designed to run anything you throw at it. No. A microcontroller is a specialist. It's what we call an embedded processor. It's built to do one job and one job only for its entire life. It doesn't need to check your email. It just needs to run the microwave or control the printer or deploy the airbag. That's it.
All right, so there are thousands of different kinds of these embedded brains out there. But for this explainer, we're going to focus on a true classic, an icon, really, one that helps shape the world we live in today, the 8051. It's the perfect way to understand how you can pack an entire computer onto one tiny sliver of silicon.
And this right here, this is the genius of the microcontroller. See, a normal computer like your desktop is built in pieces. You've got the main brain, the CPU, but then the memory, the storage, and all the ports to plug stuff in, they're all separate parts on a big motherboard. But a microcontroller like the 8051, it takes all of that, the whole shebang, and crams it onto a single chip. And that makes it super small, super efficient, and super cheap, which is exactly what you want for putting it inside another device.
So just how much power are we talking about here? Well, the original 8051 had 4 kilobytes of ROM. Think of that as its permanent instruction book. To put that in perspective, a single photo from your phone is thousands of times bigger. And get this, it had just 128 bytes of RAM. That's its temporary scratchpad for thinking. That is an absurdly small amount of memory. But for a single-minded job like running a coffee maker, it's all you need. That incredible efficiency is the whole point. Okay, so we've got this tiny, super efficient computer. But how do we actually write that instruction book that tells it what to do? You know, the one that has to fit in just 4 kilobytes? Well, to do that, we have to learn to speak its language. Deep down, at its core, the chip only understands one thing: electricity. Is it on or is it off? We represent that with binary code, ones and zeros. But trying to write a program as just a gigantic string of ones and zeros, that would be an absolute nightmare for any person. So thankfully, programmers came up with a much more human-readable shorthand called assembly. And this is a perfect example of what assembly language looks like. Instead of a mess of ones and zeros, you get a simple command like this: move A #55H. Let's just break that down really quick. Move is just short for move, pretty simple. A is a special little storage spot right on the chip. Think of it like the main memory button on a calculator. We call it the accumulator. And #55H is just a number written in a way the computer gets. So all this one line is saying is, hey, take the number 55 and put it in that main temporary storage spot. That's it. A single, clear instruction for our little computer brain. Now, obviously, moving one number just one time isn't all that useful. The real magic, the reason these little chips can run our appliances all by themselves, is their ability to repeat tasks over and over and over again. And that's where programming loops come in. They are the absolute bedrock of almost everything these embedded systems do. So let's see how we can build a really simple loop. First step, MOV R2 #10. This just tells the chip to put the number 10 in a different little storage box, which we'll call our counter. So our counter is set to 10. Next, we have the action we want to repeat, add a #3. This just adds the number 3 to that main storage spot we talked about before. And third, and this is the magic part, is the command DJNZ. That stands for decrement and jump if not 0. It tells the chip, okay, subtract 1 from the counter. Is it 0 yet? No? Great. Jump back up to the again spot and do that add command one more time. It's going to keep doing that again and again exactly 10 times until our counter finally hits 0. And just like that, you've created a simple automated task. Okay, so the chip can follow instructions and it can repeat them. That's great. But all of that is happening inside the chip, in the world of pure logic. How does any of that internal math actually do something in the real world, like turn on a light or read a button you just pressed? Well, that connection happens through its input ports, or I/O for short. These are the actual physical pins sticking out of the chip that connect to everything else in the device. You can really think of them as the chip's senses and its limbs. An input port is like its sense of touch. It can feel if a button is being pressed. And an output port is like its voice or its hands. It can send a signal to light up an LED, spin a motor, or make a beep. Our old friend the 8051 is pretty well equipped here. It has 4 of these ports, conveniently named port 0, 1, 2, and 3. Each one of those ports has 8 pins. So you do the math, that's a grand total of 32 individual lines that it can use to either sense the world or control it. That's more than enough to handle all the buttons, lights, and motors on something like a printer or a security system. So let's just step back for a minute and look at the big picture here. We started with this idea of a hidden brain, and now we've actually seen how a single chip can be a whole computer, how we can give it commands with a simple language, and how it uses those commands to actually interact with the physical world. So what's the most important stuff to remember? Well, first, that microcontrollers are these amazing all-in-one computers on a chip. They're built for just one dedicated job. To do that, they pack everything they need, CPU, memory, and connections into one tiny cheap package. We can use simple instructions to build powerful automated loops, and they connect that logic to real-world actions using their I/O ports. They are, without a doubt, the invisible workhorses that power our modern lives. It's pretty incredible when you think about it. From the simplest kid's toy to the most advanced piece of medical gear, these little chips are everywhere, just quietly and reliably doing their one job. And it really makes you wonder, as they keep getting more powerful and even smaller, what amazing new things are we going to teach them to do next?